So, in today's class, we are going to be talking about memory organizations as well as the architecture. And we are continuing from where we ended. That the previous topic, we're talking about the architecture of the computer, how the computer was designed. So in today's lesson, we are talking about the memory, how it has been designed, following the course outline. So let's now get into it. Right. So what is a computer memory then? Then a computer memory is basically a hardware device used to store data, information, or instructions temporarily or permanently. So any device that is there to store information, instructions, data that the computer is working on, whether it's going to be for a short time or for a very long period of time, that is considered to be a computer memory. So a computer memory is also being referred to as a brain of the computer. So I mean of a human being. We people have also specific memories. We keep our information in our memory. You keep that's why we say we have memories, because you remember things. There are some things that happen now, and after a few minutes you forget about what you were talking about or what you were doing. And there are some things that are even that happens from a very long time when you're a child or something like that, you still remember them. So it also works the same as a computer memory. We have devices that store information for a very long time, and we also have devices that store information for a very short time. So a computer memory, we are going to be looking at. So we'll be looking at one, the computer memory. We are looking at registers. Okay, we'll be looking at cache. We'll be looking at primary memory as well as the secondary memory. So in this way, this is how memory is placed. So registers are usually next or within the CPU, and then come closer to the cache, the primary memory, and the secondary memory. So without wasting time, so let's get to it. Starting with the primary memory. Then what is a primary memory? Okay, primary memory, this memory is used to keep programs or data when processors is active to use them. Meaning when the processor means the CPU. When the CPU is active, when the CPU is working, when the CPU is doing some execution, that means now it keeps information in the primary memory. Okay, so the primary memory it's then called main memory, which is classified into a random access memory, and this is the random access memory. It's very well known as a RAM. So it keeps the information, and this is how it looks like. And then we have now the read-only memory, and this is how it looks like. That is called a ROM. So let's look into each and every primary memory, starting with the RAM. RAM is actually stands for random access memory. Why is it then called random access memory? Because the processor can literally it can actually access data or instructions randomly everywhere. They are not stored in a structured way. They are stored everywhere. And the CPU can actually access that data on the RAM anyway. Okay, so your computer RAM is essentially term memory where data is stored as a processor needs it. And again, adding on that, it's a volatile. And volatile actually means that as soon as the power goes off, you lose everything, because the RAM works only when there is power. As soon as the power goes off, then you lose all the information that was stored there. So like what in the beginning when I explained that the primary memory keeps the information when the processor, okay, when the processor is active, and the processors are always active when there is power. And as soon as the power goes off, then just know that you lose everything, because that is how the random access works. Okay, then now we have two types of RAMs. Okay, we have two types of RAMs. We have a dynamic and we have a static. Okay, we have a dynamic and we have a static. So a dynamic RAM, this one, it's actually, it's a combination of capacitors and transistors. And it's a dynamic because then it needs to be refreshed all the time with electricity. Okay, it needs some electrical power to be refreshing it and to be loading data within the RAM. And that makes it actually to be a bit slower compared to a static. The static one, although it's expensive and it lasts very long, it's actually, it doesn't require any refreshment. It doesn't require some electricity to be um, um, refreshing it. Even if this one consumes less power, it consumes less power, just know that it needs some electrical charges so that it can be refreshing all the data that are going in the RAM. And these are the two RAMs that we have. This is how they look like. We have a dynamic, which is actually the RAM. This is what we are used to. We see this all the time. This is the RAM. And then we also have a static. It's also there on the motherboard. You'll be able to see it. So this is how it looks. They look like. Then now we come to the second one. These are the two types. Remember, we are talking of primary memory, of which is a RAM and the ROM. So we spoke about the RAM, which is a dynamic access memory, which stores information for a temporarily. As soon as the power goes off, you lose your information. And we have two types of RAMs, which is actually the dynamic as well as the static. Now, when it comes to ROM, ROM stands for read only memory. I want you to understand this term, read only memory. So you write there, you read, you read from the memory. And this one is actually a non-volatile memory. It's not volatile, so meaning even if power goes off, you still have to keep your information. But again, it's needed by the CPU. When the CPU is actually in work, then it is needed. It stores those information permanently on the chip. So the memory does not depend on electricity, like what I said, to save instruction. Instead, data is written to individual cells using binary code. So you see why it doesn't need electricity is because data has been written on the RAM, on the chip itself, using binary codes. Then here comes now RAM contains some important instructions or programs that are required to start or boot a computer. So when you are restarting your computer, those instructions are kept in the RAM. Okay, in the ROM, pardon me. So that's where they are kept, in the ROM. Great. So we have spoken about ROM. ROM also have its own types, okay, just like RAM. So even ROM have its own type, and let's look at them. So we have 5 types of ROM. Okay, we have 5 types of ROM. The first one is called must read only memory. So with must is the oldest type of read memory whose programs and data is pre-configured by the integrated circuit manufacturer. The integrated circuit, that chip and the motherboard, whoever developed that, they pre-configure or they pre-write those instructions on the chip themselves. When it comes to programmable read-only memory, This one, it's a digital read memory in which a user can write any types of information or programs only once. What it's trying to say, once you get the circuit, once you get the chip, you write your instructions, or you write your whatever thing, data that you want to write on that circuit. You only do it once, and that's it. Okay, you only write there once. You insert your circuit on the motherboard, and that's it. When it comes to erase and program and the programmable only read-only memory, is a type of a memory in which it stores data can be erased and reprogrammed only once. So meaning that you can actually write something and you can only erase once, and then you reprogram again. So meaning you can rewrite some instruction set on that circuit again, but you can only erase once. Okay, and then here comes now the electrically erasable and programmable read-only memory. With this one, it's actually erasable, and it's read-only memory used to erase stored data using a high voltage electricity charges and reprogram it again. So this one you can actually use electricity, you erase, and you'll be able to reprogram again, as long as you delete or you erase data using the electrical charges. Now the uncommon one, this one is the flash ROM. The flash ROM is a non-volatile memory chip that can be written program into small unit of block and set. So with this one, it's a bit smaller because you only you write into small units. It's unlike the other one, the others that are written on the whole circuit, but here you use the small unit. So let's look how they really look like. So this is how they actually look like, and this is the ROM, and then we have the PROM and the EPROM and EEPROM. So this is how they actually look like. So if you see them on the motherboard or anywhere else, so be able to identify them, that is how they look like. Okay, then we come now to secondary memory. So we are done with the primary memory, of which is two types, the RAM and the ROM. Then we come now to secondary memory. That was a primary memory. This is the secondary memory. Now the secondary memory is these are storage devices. They store this one store data for a very long time, and they don't require electricity or start up to store this information. And again, a CPU can be active or can be inactive, and this information will still be able to be retrieved. You'll be able to get your information, and these are the types of devices that are referred to as a secondary memory. Okay. So what we have here now is actually the US. This is what we call a smart card. I know this is what we call a memory card. I know many people we call it memory card, especially within our country. We call this a memory card, which is also referred to as SD card. And then here comes now to a USB. Okay, and we have a hard drive. A hard drive can either be internal or can be external. So, and we have the CD, we also have flop disk, tapes, magnetic. So we have a lot of them. Okay, these are not the only one, but these are common used one. I know we are going out of CDs. CDs are these days are not really commonly used, but I know these ones kind of every student have a USB or either a card. Okay, so these are the ones that are referred to as a secondary memory. Okay, so we need now to move to another memory. Remember when we saw on that computer memory, we saw we have registers, we saw we have cache, we have primary, secondary. We have spoken about the primary and the secondary. So let's go to the next memory, which is called cache memory. Now with the cache memory, okay, the cache memory is a small size chip based on the computer memory that lies between the CPU as well as the main memory. So what it does is it makes retrieving data from the computer memory more efficient, okay, more efficient, more faster, okay, between the CPU and the main memory. Initially, data comes from, we all know that information as RAM keeps programs that the CPU is working on. But instead of the CPU now coming to get information from the RAM, there are chips in the middle there, or there are memories in the middle there that help to retrieve information from the RAM to the CPU. Okay, so it acts as a temporary storage area that the computer's processor can retrieve data from easily. So let's look at the demonstration, how it works. So here is the RAM. Okay, so this is the RAM, and it keeps all the programs that are the CPU supposed to be working on. Now, this RAM keeps also information and everything else that is coming from the input and output devices, as well as from the secondary memory. So this is where it comes from. Now, after that, then information needs to be retrieved from the CPU. So when the CPU is working on a specific program, that program is actually where? In the RAM. Okay, so it retrieves it from the RAM. So this is where it gets it from. But now this distance it's not efficient for the CPU to be getting instructions from the RAM, and also the RAM to be giving instruction to the CPU. So that's why there is a middleman here that is called cache memory. Okay, with a cache memory, then it makes it easier for information to come from the RAM, then it being stored in the cache. Then that is how then the cache will be giving the information to the CPU, and that makes it easier now also for the CPU to access the information into user, instead of using this very long distance. I'll call it a distance because of this image here. So it will be it's not effective enough, it's not efficient enough, and it will be very slow by the time it gets information from the RAM. So that's why there's a cache in the middle, and that is how it works. So it gets information from the RAM, and then the CPU will be able to fetch information here from the cache memory. So it's just for easier and faster way of retrieving information. Okay, so we are done on that, and this is how now the cache memory looks like on the motherboard. If you see a small chip like this, let me just show you. Okay, so I didn't have that image. So if you see a small chip like this, you always find it. Sometimes it's just almost next to the CPU. You'll find two of them. There are times that you find two of them cache memories. So if you find a chip like this on the motherboard, just know that that is a cache memory. Now we have a way of we have types of cache memories. I know we have level 1, 2, and 3. Those are the types of cache memory, and comparing depending on their fastest. The one that is faster is the one that is close to the CPU, and the one that is not faster, which is level 3, is the one that is closer to the RAM. But all in all, they are all cache memory. But then there is a way of then data flows from the cache memory to either the CPU or to the RAM. So we have a fully associated, okay, we have fully associated cache memory. So meaning that with a fully associated, so data then are stored here or can be retrieved from any line. Okay, so if we have 16 lines, that means that then the data needs to be looked at 16 lines to search for them. And then we also have direct. With a direct, a specific data is stored only on that particular line of within the cache memory. That's where it's actually kept. It's actually a direct. So when data is being looked, it does not need to go through all these 3 lines. It just needs to come to one line, which is a direct, and this is where it's going to get its own information. Then we have the middle one, which is the NY set associative. With the NY set, it means that the lines are not really direct, and also they are not fully associated. So the lines that needs to be looked at, of course, it's not just going to be one line. And again, it's not going to be a lot of lines like in a fully associated. They have very few. So that is how the information can actually be retrieved. Like how it's saying that with a fully associated cache, every memory location can be cached in any cache line. So in any way, like how I explained in the previous image, so that is a fully associated. And then in the direct, cache memory locates maps to a single cache line with a direct. But in the NY set, the most common cache implementation, memory address can be stored in any line of the cache. It can be in any line, meaning either it can, as long as it's not going to be on the fully cache, but it will be in between there, not exactly the direct, and it's not really going to be the fully associated. Now, after talking about the cache memory, we are now going to look at the last memory within the memory hierarchy of the computer, which is a register memory. Now, with a register or registers, I should say registers, these are the smallest data holding elements that are built onto the processor itself. These are the memory locations that are direct accessed by the processor. Because why? They are within the CPU. This is how a CPU looks like, okay? On the motherboard, you see it. I know some of you, I have already shown you when they had a class face-to-face, but to those who did not see, we are still going to see them after the break. So this is how the CPU looks like, okay? This is how the chip looks like. Now, remember when we're talking about the architecture of the CPU or the John von Neumann architecture. So in this case, that CPU is not just a chip on its own like that. This is how it looks like inside. So within the CPU, the central processing unit, we have logic units, we have arithmetic logic units, and then we have registers. So this part of the CPU, it's a memory. So within the CPU, there is a memory here that is called the registers, which are, we have one, which is program counter, and then we have the accumulator, and we have memory addresses. All these are the registers, and they keep information or instructions that the CPU is directly working on. So this is now the register. So what we have a secondary memory, we have a primary memory, we have a cache memory, and then now we have registers that are on the CPU. Okay, so these are the types of the registers, memories. We have a memory address register. This memory address register holds the memory location of data that needs to be accessed. It holds the memory, okay? And then we have a memory data register. So this is the address register, and then we have data, whole data that is being transferred to and from the memory. The data that needs to go to the CPU, and the data that needs to go to the memory. So that, and then we have accumulator. This one now is the immediate arithmetic and logic results are stored within the accumulator. Comes now to the program counter, and this one contains the address that of the next instructions to be executed. And then we have current instructions. This one is the one that is being processed that time. So it's stored within the current instruction register. I hope that does make sense. So now this is how the hierarchy looks like. This is where the CPU is. And of course, this is the outside environment. This is the users now. So with the CPU here, and these are the users. So this is how the hierarchy is. The access by the CPU as well as the storage increase, the increasement. So this one is a small capacity, then a bit small capacity, then a little bit small capacity, and then we have a bigger capacity. So this is how the hierarchy of our of our memory looks like. Now, after knowing that, how does memory works? Let's look at it. So we have, before I tell you about memory addressing, I want you to understand how memory looks like in the computer. This is how memory looks like. So it looks like this table here. It's like a very long table, and that table is divided into small cells. These are what we call now the cells. Now these cells, they can be a lot. Now within the cell, this is where we store the values. Okay, this is where we store the value. We have one side which is for operands, the first, and then we have the other side which is the operators. So that is actually how the operand are called, and then we have the operands where we keep the value, as well where we keep the arithmetic operands. So this is where we keep all the values. And if from here to here, this is the one that is called the cell size. So this is the cell size. Now, these cells, they have numbers. They are allocated these numbers, and those numbers are the ones that are called an address. Like this cell is actually at address what? Address 0, and the list goes on. They are very huge. So this is basically how memory works. So information is what? Or values are kept within the cells and depending on the addresses. So this is the memory, which is basically the RAM. I can put it that way. Okay, so this is how they are kept. But when it comes to the register, it doesn't look like this, but this is how, if we can just go back here. So this is just how it looks like. The register, this keeps the information here, the accumulator, and so forth. That's how they look like. But in the memory, that is exactly how the information or the values are stored. Now, talking of that, so memory addressing or memory address is a unique identifier used by the devices or the CPU to track data. How will you track data? You need to know which operand, and then of course this is the address as well as the value that is stored in here. I think one cell is actually just equal to 1 byte or 1 bit. I should say it's equal to one bit. And in the memory, we call it words. When they become 16, you have words. Okay, you have a word, so this becomes a word, and this is how the information is kept. So when you're addressing, it's like you're just tracking where to find a particular data, or where to find particular way in which value, what is the value in which particular cell. Okay, so memory addressing are usually allocated during the boost process. When the computer is turning on, this is when now the addressing is being performed. We have schemes of addressing or mode of addressing. How to track. Remember, addressing is tracking values within or data within the memory. Okay, I want you to know that addressing is just mode of tracking data within within the memory, either by the CPU or by other devices. How do they track particular data in the CPU? We have one, there are a lot, but I'm just going to mention a few of them. One, we have a direct addressing. With a direct addressing, then this scheme is in which now the address specify which memory word or register contain the operand. Okay, which memory, which cell, okay, have contain a specific operand. contain a specific data. Which one? So that is a direct. It have a specific direct container or register. In this case, when you see here, this is a direct. For example, this is 1. So this is a direct address that contains data. And then we have indirect. With an indirect, it's a two-way. So with a direct, the processor can just access the memory once, because it goes to that direct cell or address it needs to get that particular data. With an indirect, though, with this mode or scheme, it specifies which word or register contains, and not the operanda, but the address of the operanda. So meaning that first, it needs to look at which memory is it. After looking at which memory is it, it also needs to look at the address, which value is that which memory and which value is it in the memory. Okay, then we have index. With the index, it has two parts also. They have a number of index, the register and the content. What is in that particular cell, and then also the address of the operanda in the sum of the content and the contents of the index register. So it uses the index, it contains index, which is a direct address, and then it also contains the index of immediate addressing and the indirect addressing. So with this one, it has two. So this is where you can actually understand, because it works with the index for direct addressing, as well as you have indirect addressing, and then we have immediate addressing. So it's a combination of a lot of index. That is how you will be able, the computer get to access data within the memory. Now, when it comes to stack addressing, instructions with no addresses used in the conjunction with a stack. This is when you have instructions and they don't have an address, or the address is unknown, then they are just stack, okay, addressing. Okay, this in form of addressing specify that the two operandas are to be popped off the stack, one after the other. The operandas performed and the result pushed back to the stack. So it doesn't have the specific address. It's not like in all the addressing, either direct, indirect, or index, you'll find there's a specific address that data can be allocated to. In this case, there's no specific address. So instructions are being pushed out of the memory. Okay. So these are the 4 that I've mentioned. Like I said, there are a lot. Just go and read further on the addressing. Okay, so that brings us now to know that to the memory of units. You have memory of you have units of the memory, and with these units within the memory itself, the main memory, we have 2. Okay, I mean they're actually 3. We have a byte, you have a word, and then you have a double word. So these are the memories. The main memory storage unit is byte, word, and the double word. So a byte is just 8 bits. When it comes to a word, it's actually 32 bits, and the double word, you actually find a 64 bits. So this is a memory for the main memory. And then for the secondary memory, or the high level storage, we have these are the units. Okay, from the kilobytes, megabytes, gigabytes, as well as the list goes on. There are a lot. There are not really that many, but these are the commonly used ones. So you can actually convert your kilobytes to megabytes, megabytes to gigabytes, gigabytes to terabytes. And when you're converting in that sense, when you're converting from a bigger number to a smaller number, you just need to multiply with 1024. But when you are coming from a bigger unit, a smaller unit to a bigger unit, you need to divide with 124. I repeat, when you are coming from a bigger unit to a smaller unit, you just need to multiply with 124. But when you are coming from a smaller unit to a bigger unit, you need to divide. In another word, when you're coming from kilobytes to megabyte, you divide. From megabytes to gigabyte, you divide. From gigabyte to terabyte, you divide. From terabyte to petabyte, you divide. And you divide all those with 1024. But when you're coming from petabyte to terabyte, you multiply. From terabyte to gigabyte, you multiply. From gigabyte to megabyte, you multiply. From megabyte to kilobyte, you multiply with 1024. And this brings up now the round of our computer memory. Now, just to give you a recap of what we discussed about the computer memory, remember we have 4 types of memories, of which we have a secondary memory, although we started describing primary memory, and when we described the secondary memories, and then we also described now the cache memory, which follows the primary memory, and we ended with registers. And with the registers, there are types of registers. Within the register, we also have spoken about the addressing memory. Okay, how to locate data within the memory. So that brings us now to the round of this unit, which is the computer memory. So thank you. I will see you in the next unit, of which we are going to talk about the input and output subsystem. Until next time, ciao, ciao.